Hello, myself Dr. BJD Kalyani, working as Associate Professor in the Department of Computer Science and Engineering of Institute of Aeronautical Engineering. In this video, I will discuss problems related to memory organization. So, memory is basically used to store the information, programs and data. So here the main memory is generally referred as primary memory, which is connected to the CPU directly, and it is categorized into RAM and ROM. The secondary memory is generally used to extend the storage capacity of the computer. So here various auxiliary devices can be used like the magnetic tape, magnetic disk, hard disk, flash memories, are the various category of auxiliary storage devices. So how these organizations with proper addressing and referencing mechanisms, how memory mapping between various memories has to be taken place, and what are the various access mechanism of the memory. The problems related to these topics can be discussed in this video. The first problem statement is, how many 128 by 8 RAM chips are needed to provide a memory capacity of 2048 bytes? How many times of the address bus must be used to access this 2048 bytes of memory? How many these lines will be common to all chips? How many lines must be decoded for the chip selected? Specify the size of the decoder. So here the total addressing capacity of the memory is 2048 and it is of 128 by 8 RAM. So here 2048 by 128, total number of memory chips required is 16 chips. And to address these address capacity of 2048, 2 power 11 is equivalent to 2048. So 11 address lines has to be required to address a memory of capacity 2048 bytes. And here it is a 128 by 8 RAM. So 2 power 7 is 128. Total 7 lines to address the each chip. And here in the 11 lines of address, 7 lines are used for address of each chip. The remaining 4 lines can be used for decoding of 16 chips. Total 16 chips are there. 2 power 4 is 16. So 4 lines are used for selection lines for the decoders. So the decoder can be the 4 by 16 decoder size. A computer uses RAM chips are 1024 by 1 capacity. How many chips are needed and how should their address lines be connected to provide a memory capacity of 1024 bytes? How many chips are needed to provide a memory capacity of 16k bytes? Explain in words how the chips are to be connected to the address bus. So 8 chips are needed with address lines connected in the parallel. And here 16 by 8 is equal to 128 chips. 16k bytes has to be providing the capacity of the memory. 8 chips has to be used. So 16 into 8, 128 chips can be used. Use 14 address lines, that is to address the 16k. 2 power 14 is 16k. So 14 address lines can be required for this memory. And here 10 lines are used to specify the chip address. So in the 10 lines for the address and only the 4 lines can be used to decoded 16 chip selected input. So to address 1024, 10 address lines are needed and remaining 4 can be used for the selection of the chips. Next, a computer employs RAM chips of 256 by 8 and ROM chips of 1024 by 8. The computer system needs 2K bytes of RAM and 4K bytes of ROM and 4 interface units, each with 4 registers. A memory mapped I/O configuration is used. The two highest order bits of the address bus are assigned 00 for RAM. RAM address is 0001 for ROM and 10 for interface registers. How many RAM and ROM chips are needed? So here the capacity is 4096 by 128, that is the 32 RAM chips. Okay, 4K bytes of RAM. So it can be the 4096 by 128 32 RAM chips. And 4096 by 512 is equal to 8. 8 ROM chips are available. And here to address 4096, 2 power 12 is equivalent to 4096. So 12 common address lines has to be required for the memory and one line to select between RAM and ROM. Only 2 chips are RAM and ROM are available. To select either RAM or ROM, one line, selection line can be required. Next, an 8-bit computer has a 16-bit address bus. The first 15 lines of the addresses are used to select a bank of 32K bytes of memory. The higher order bits of the addresses is used to select a register which receives the content of the data bus. Explain how this configuration can be used to extend the memory capacity of the system to 8 banks of 32K bytes each for a total of 256K bytes of memory. So the processor selects the external register with an address of 8000 hexadecimal. Each bank can have 32K bytes and are selected with addresses 000 to the maximum address 40 to the maximum address 7FF. The processor loads an 8-bit number to the register with a single 1 and 7 zeros. So each output of the register select one of the 8 banks of 32K bytes through a chip selection input. So a memory bank can be changed by changing the number of registers so that the selection to the chip can be varied in order to vary the memory capacity. A magnetic disk system has the following parameters. Ts is the average time to position the magnetic head over a track. R is the rotational speed of the disk in revolutions per second. Nt is number of bits per track. Ns is number of bits per sector. Calculate the average time T that it will be take to read one sector. So here the disk can have the architecture. The disk is made up of concentric circles. Each circle can be referred as the track. And it has to be divided as the parts. And each part can be taken as the sector. And here magnetic disk is collection of multiple disks. So the hard disk drive can have multiple disks and are connected over a spindle, and here the read-write head can be there. These disks are rotating. Whenever the surface comes under read-write head and touches that part can be magnetized, then the read-write operation can be taken place. So here TS is average time to position the magnetic head over a track. Here this is the time required to position the head. The spindle speed, rotation speed of the disc can be the R. NT is number of tracks and NS is number of sectors. So calculate the average time T that will take to read one sector. So average time is equal to TS plus time for half revolution, time to read a sector. So here TS 1 by 2R, 1 revolution, R is the RPU for revolution speed, 1 by 2R, NS by NT into 1 by R. This is the average time. Next, what is the transfer rate of an 8-track magnetic tape? Number of tracks is 8. Whose speed RPU is 120 inches per second and whose density is 600 bits per inch. So the transfer rate can be calculated. So an 8-track tape reads 8 bits, 1 character at the same time. So transfer rate is 1600. That is the density of the disk into 120, that is the speed, revolution speed. So total 192,000 characters can be read. Next, obtain the Boolean function for the match logic of one word in an associative memory, taking into consideration a tag bit that indicates whether the word is active or inactive. So here, instead of accessing the memory by address, accessing the memory with content can be done with the help of associative memory. For this, the search word has to be required a match logic. So, the match logic of one word in an associative memory, taking into consideration a tag bit that indicates whether the word is available, active or inactive in the associative memory. So here the match logic can occur at the required time interval Ti is equal to 1. So here with the AND gate, the match logic has to be implemented. So Mi is the match bit, Ti is the search bit. So Mi Ti multiplication is the match logic. So when this produces as 1, the word is available in the associative memory. So this is the Boolean function. What additional logic is required to give a no match result for a word in an associative memory when all key bits are zeros? So if the key is all 0, no match logic has to be represented in the associative memory. Why? Because associative memory, the another name is content addressable memory. So here we have to check for each value, at least one key must be the 1, then only the match logic can be implemented. So this is the M logic where the word can be searched is found or not. Depending upon that, the Boolean function can be implemented, the match logic can be implemented with the AND gate. So it has to multiply with the key value summation. So the key, if any one key is 1, then only the word is present in the content addressable memory. Next, a virtual memory has a page size of 1K words. There are 8 pages and 4 blocks. The associative memory page table contains the following entries. The page table: page 0, black 3, page 1, black 1, page 4, black 2, page 6, black 0. Make a list of all virtual address in decimal that will cause a page fault if used by the CPU. So, the pages that are not in the memory can be the page 2, which is of 2K address. Why? Because the memory is of the size 1K words. So, at the page tip only 2K address that will cause starting with 2042 482 3074. Next, at the page 3 is also the page fault can occur. At page 5 is also the page fault occur. Why? Because the page 4 can start at the black 2. And at the page 7 also the page fault can occur. The page fault when occur, the required page cannot be loaded at the memory addresses. But it is the page size can be the 1K word. And the page table that are loaded in the memory can be these blocks and these pages. So that's why at the second and third and fifth and seventh are the missing pages in the memory so that the page fault can occur. Next, a two-way set associative cache memory uses blocks of 4 words. The cache can accommodate a total of 2048 words from the main memory. The main memory size is 120K by 32. Formulate all pertinent information required to construct the cache memory. What is the size of the cache memory? Main memory size is 120K by 32. So 120K means 2 power 17. So the set size of 2, the index address can be 10 bits to accommodate. So, and it is 2048 words can be accommodate the cache size. By the 2 is the size of the set size. So 1024 words in the cache it has to accommodate. So that the tag field can accommodate these 7 bits for the tag and the 10 bits for the index. So this is the address mapping. So the block is 8 bits and the word is 2 bits. So here the size of the memory can be 10024 into 2 plus 7 plus 32. So here in a set associative mapping, 2 sets has to be designed. So here 7 bits is the tag field and the data can be the 32 bits. So here 128 by 32. So the data can be of 32 bits. So number of sets are 2 and each set the tag is representing 7 and the plus 32 bits to represent to hold the word. So here total size of the cache can be 1024 words into 2 into 7 plus 32. So total is 1024 into 78 is the size of the main memory. Next, an address space is specified by 24 bits and the corresponding memory space by 16 bits. How many words are there in the address space? How many words are there in the memory space? If a page consists of 2K words, how many pages and blocks are there in the system? So address space is 24 bits, 2 power 24, 16 memory megabytes is the words Memory space is of 16 bits, 2 power 16, 64K words. So the size of each page has to be, number of pages can be decided with 16 by 2K. It is 8K pages are there. And each page has to be divided this 64K by 2K. The total of memory space with the 2K of the word size. Then 32 blocks can be accommodated. Next, the logical address space in a computer system consisting of 128 segments. Each segment can have up to 32 pages of 4K words in each. Physical memory consists of 4K blocks of 4K words in each. Formulate the logical and physical address formats. So logical address is 7 bits. The segment has to represent 7 bits and the page is represented 5 bits, word is 12 bits. So here the segment is of 128 segment. Each segment is up to 32 pages and of 4K words. So to represent the each, here 12 bits are required to represent the word and to point the page 5 bits reference can be used. The segment 128 segment. So it is of 7 bits required to locate the segment. So total 24 bits can be used for logical address. But in the physical address only word and block reference can be used. So they can be divided into 12 bits. Next, a processor can support a maximum memory of 4 GB where the memory is word addressable. The size of address bus of the processor is at least dash bits. The maximum memory is of 4 GB, 2 power 32 bytes. Hence, one word is 2 bytes. Total number of words is 2 power 32 by 2. So, 2 power 31. So, address of these words required minimum of 31 addresses. Next, how many addresses and data lines will be there for a 16M by 32 memory system? Since there are 60M words, the number of address lines will be 24. 2 power 24 is the 16M. The word size is 32. So, the data lines will also be 32. Next, for a 2K by 16 memory system that uses a decoder to select a word, the total number of external connections to the memory system, including address, data, control and power signals will be at least. There will be 11 lines of the address in order to point the 2K, that is the 2 power 11 is equal to 2K. And 16 lines for the data. So 2 lines for the power supply, read and write lines 2 lines. So total 31 lines are required. Next, assume that a 1 GB by 1 dynamic RAM memory cell array is organized as 1M row and 1K columns. The number of address bits required to select a row and column will be. So this is 1M row. The number of row address lines can be the 2 power 20 is equal to 1M. So 20 can be required address lines. Also selecting 1K columns, the number of column address lines can be 10. 2 power 10 is 1K. So total 20 plus 10, that is the address lines and the column lines. To build a 1 GB 60 by 16 memory system, the number of 256 M by 8 memory modules required would be. So here the 4 into 256 is the 1 GB and 2 into 8 is the 16 word size. Hence, the number of memory modules required will be 4 into 2, that is the 8. If a memory has 10 address lines and the size of each addressable location is 4 bytes, then what is the maximum storage capacity of the memory? So, number of address lines 10. The size of each addressable location is 4 bytes. So, maximum storage capacity is 4 into 2 power 10, that is 4 KB. Describe in words and by means of a block diagram how multiple matched words can be read out from an associative memory. So, associative memory is content addressable. How the match logic has to be implemented in the associative memory. So, a D-bit counter derives a D to M line decoder where 2 power D is equal to M. So, with the help of match logic, the M into the register read has to be taken place with the help of AND gate. So, M match register has to be stored in a vector to search for each word, and it has to attach to the each cell of the associative memory. And to activate the decoder, the AND gates for whenever the match and key value is 1. So, to equate that, the D by M decoders has to be required. So, here no number of words in the memory. For each count, MI bit is checked, and if it is 1 only, the searched word can be matched in the memory. So, the corresponding read signal has to be activated with the help of D by M decoder and with AND gate logic. Next, the access time of a cache memory is 100 nanoseconds. And that of main memory is 1000 nanoseconds. It is estimated that 80% of the memory requests are for read and the remaining 20% for the write. The hit ratio for read access only is 0.9. A write-through procedure is used. What is the average access time of the system considering only memory read cycles? What is the average access time of the system both for read and write request? What is the hit ratio taking into consideration the write cycles? So, here the 0.9 is the hit ratio. 0.9 into 100 is the cache access 100 nanoseconds plus 0.1 into cache plus memory access 11,000. So, this is equivalent to 90 plus 110, that is 200 nanoseconds to perform the read operation. And to perform the read and write operation, 0.2 into 1000 plus 0.8 into 200 nanoseconds to access from this A, the 200 for the read cycle. So, it should be the 360 nanoseconds. So, hit ratio is the 0.8 into the access of the cache can be the 0.9. So, it can be 0.72. So, these are the questions that are related to the memory organization taken from the textbook Computer Systems Architecture by Maurice Mano. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.